Okay, guys, here we go. The next video, we're talking about graphing logarithmic functions, and really it's very analogous to what we did in the previous section with graphing exponential functions. We have the same kind of transformations, and also just graphing function in general, right? Where here you have the A, B, C, and D. Again, we're using capital letters because little a is already taken as the base. So what does A do? A is a vertical stretch multiplied outside of the overall function. After all the logging happens, you cut down all your trees and then you multiply by A. Okay, the B is close to the X. It happens before the log function is applied, right? So close to the X means it's a horizontal, either shrinking or stretching. And which one is it? Well, the easiest way to remember to me is just take the reciprocal, whatever b is. Like if b, let's say b was equal to 2, the reciprocal is 1/2. 1/2 is a shrinking, right? You're shrinking by half. Or let's say b was a half, then a reciprocal would be 2. So that's a stretching, and it's a horizontal stretching by 2. That's the easiest way to remember to me. And then c also close to the x, right? It happens before any function is applied. So you subtract before, then that's going to be a horizontal shift to the right. If you add, it's a horizontal shift to the left. And then finally the D. D is on the very outside. If it's positive, move up. If negative, move down. To me, that's the most intuitive one of all of them. Okay, so those are the translations. I kind of just went through them quickly. Transformation, sorry, because we've seen these before, right? Both in chapter 1 and in the previous section. And with that, let's just get to the graphs of our logarithmic functions. Grab these guys. Paste that here. Okay, starting with the two basic functions, right? Just no transformations at all. Just trying to get a feel for what does a log function look like, and here, what does the log look like when it's a fraction that's less than 1, right? One of them should be, this one should be increasing, this one should be decreasing, right? And I think I mentioned before, right? It should look like general picture, the very general sketch, like something like this. You know, logs are known to increase forever, but increase very slowly. In fact, like if you're into like computer science or you're programming something, a lot of times you're concerned with how fast programs run. And one of the measurements is like a log. And if your program runs with log time, that's considered very good. But anyways, you know, let me start for this one making like a simple XY table. Like, you know, that's always the go-to if you're kind of stuck, you don't know what to do. Just make your XY table. It's not recognizing that's a vertical line. Okay. Oh, what? Why are you so crooked? Okay. What? Oh, you know, I think my first line was not vertical. That's why. There you go. Okay. That is still, what is happening here? You know, it's my XY, I think. That was the issue. My XY were so off. Okay. So, here, y is equal to log base 2 of x. Okay, that's the function I'm gonna write. So, side note, that means, just to remind you, 2 to the y is equal to x, right? Okay, interesting. Well, you know, this guy is a inverse function of that, what I just wrote there, right? 2 to the x is actually the inverse function. So what I'm gonna do here is I'm gonna swap my variables, and for a moment I'm just gonna think about what does that old function look like? What if it was 2 to the x? Because this is an easier one to think about to me. Something we did before, right? Let's just enter a few values. -2, -1, 0, 1, 2. Okay, if I enter -2, that's 2 to the -2 is 1 over 2 to the second or 1 over fourth, right? If I put a -1, that's 2 to the -1, that's 1 over 2. If I put in 0, that's 2 to the 0, that's 1. If I put in a 1, 2 to the 1 is 2. If I put in a 2, that's 2 to the second, it's 4. This is the exponential function, right? Well, the logarithmic function is the inverse, so it's actually exactly the same values. And I just flip them. I just reverse them. Oops. Sorry, writing the wrong things. That's the 2. Yeah. And that's exactly right. And let's just do a quick check. Let's do a quick check. I cannot speak. Let's do a quick check. Is this true? Is 2 to the y equal to x here? Well, of course it is, because that's how we design it, right? 2 to the negative 2 is equal to 1/4. Check. And that's because we did it that way, right? Over here. 2 to the negative 1 is a half. True. 2 to the 0 is 1. That's true. 2 to the y. 2 to the 1 is x. 2. Correct. 2 to the second is 4. Yes. So here I have the correct data table. And I got it just by taking my original exponential function as the inverse, right? And flipping x and y. Why does that make sense? So think about how we found inverse functions before. Remember how we found inverse functions? Like back in the day? Back in the first quarter of our semester? We did it by switching x and y's and then solving for the y, right? Actually, we're going to talk about that later today. Okay, now let's plot some points. So 1, 0, obvious one. And I'm going to use purple for some odd reason. 2, 1. It's right there. Okay, 4, 2. Right there. I got -1. I'm sorry, no. 1/2, -1. So about here. And then 1/4, -2. So about there. Okay, now let's connect these dots. And your function looks something like this. Okay, this is the base function where you're starting with, and this is kind of a very typical function. Now, if I'm gonna graph a new one, I might not necessarily plot that many points. Like if I'm trying to think of translation, what I typically want to think about for sure though is this point right here, that 1, 0 point, and then maybe at least one other one. The most easiest one being this 2, 1. This 2, 1, right? Where 1 here is the power, and here this is the base. Cause like if it's 2, right? 2 to the 1 is equal to 2. If it's 3, let's say, it would be 3 to the 1 would be equal to 3. So this would be a 3. So that number you always get, right? You get the base, comma 1. That's here. Base, 1, 2, 1. And then it gonna grows slowly, but it grows. Okay. Where were we now? Let's do that. So that was 14. I forgot to write the number. Sorry, 14. Okay. Now on to 15. And I'm gonna leave some of this stuff here. Let's leave the table. Okay, here I have y is equal to, what's the new function? Log base 1/2 of x. Let's see if we can just do it directly from the table this time. So 1/2 to the what is equal to 1/2 to the y is equal to x, right? So 1/2 to the, let's do 0 right here in the middle. 1/2 to the 0 is equal to 1. So I get the point 1, 0, just like before. Yeah. Okay. 1/2 to the 1 power is equal to 1/2. 1/2 to the second power. So notice I'm kind of doing things backwards, right? Because that's the easier way for me to think about it. Think about logs. 1/2 to the second power is 1/4. I don't know why I changed the fraction styles here. It's easier to fit if I draw it this way. Okay, what about 1/2 to the -1? Okay, so that's 1/2 to the -1 is 1 over 1/2, which is flip it over to 2. Yeah. And let me just tell you, if I take 1/2 to the -2, that's going to be 4. Okay, so you notice it's kind of the same values as 2, but just sort of reverse, right? Let's draw these out. So you notice what I was saying earlier, right? When y is equal to 1, you're exactly at whatever your base is. And in this case, the base is 1/2. So at y equal to 1, you're at 1/2. So right here. Okay, at y equal to 2, you're at 1/4. So you're right here. Yeah, okay. And what about y equal to... Oh, actually, let's plot other points. So I did 1/4 2, I did 1/2 1, did 1 0. Next would be 2 -1. Okay, let's plot it the proper way now. 2 -1, and then 4 -2. When I'm plotting y first, it's kind of just awkward because we're so used to plotting our x value first, yeah. So, okay, something like this. So notice I'm decreasing the whole time, and that's because our base value is less than 1, right? It's a fraction. But still, I get all values. And this is consistent with that sketch I drew you guys in the beginning. That was question 15. Sorry, I keep forgetting to write the question number. Okay, now we're ready to forget about the tables. We're going to focus on transforming now, okay? So those first two were just kind of the base graph functions, the typical functions, how they look. Just give you a general picture. And I'm not going to bother even with these tick marks. I'm just going to draw just a very general picture. So in fact, let me do this. Down here, I'm going to write just kind of as a reference, the basic function graphs, okay? This is kind of a reminder to myself. Okay, so we'll do 1 for when the base is bigger than 1. So we get the point always 1 0, right? It goes through there like that. Okay, 1 0, still a point either case. This is where a is less than 1, but still bigger than 0. And it looks something like this. Okay, so now, okay, sorry, we have L natural log x minus 1. What's happening? This minus 1, that's a shift to the right by 1. So normally you're at 1, 0. Now I'm going to be at 2, 0. Normally you have an asymptote at right here at the center. Right? It's an asymptote right there. Let me do it so you can see that better. Asymptote is right there normally, right? Well, this new asymptote is going to be right at 1 instead. 1 over to the right. Just pretend that's straight. Okay, and then this is a natural log means e is the base. E is a number that's bigger than 1, so that's the left-hand case. So it looks something like this. Okay, and that's 16 in a nutshell. It's very rough sketch, but accomplishes things I wanted to. I can even label this point. That's 2, 0. This is question 16. That's it. Simple, right? Simple. Okay. Where's that thing? Okay, now number 17. Okay, 17, let's see what happens. So let's do them in order first. So first thing is A. A means I'm stretching upwards, right? Okay, stretching upwards by 3. Okay, just keep that in mind. Okay, and then what else? There's no horizontal stretching or shrinking, but I'm moving 2 to the left and 1 down. Okay, that's easy. So 2 to the left, 1, 2. That means my new vertical asymptote is -2, right? And then -1 down. So that, okay. Normally you would be at 1 comma 0, but now you're 1 down. Oh no, I'm sorry. Okay, this point here, first it's got to move to 2 to the left, 1, 2, and then 1 down here. Oh, wait. Does that make sense? I should do my stretching first. Oh, okay, yeah. Still makes sense. It still makes sense because this point was 1, 0. So if you think about stretching 0 up or down, 0 does not stretch. It does not stretch. So it's still going to be right there. Right there. Again, normally you look something like this, but you're just going to get steeper faster. So if normally let's say you look like this, right? Well, if I multiply by 3, it's going to be more like this. So but general shape wise, it's going to kind of look very similar. Everything just kind of happens faster and it goes a little higher than it normally would. That's what that 3 does. Yeah, but general shape wise, still looks pretty similar to the original. Okay, that was just now number 17. And if you're not so sure, just check some points. In fact, let's just real fast just confirm that we do have a correct point here. This one I'm claiming that what is this? Negative 1 comma 0 is a point on this graph. So let's just check. 3 natural log x plus 2 minus 1. So if I plug in x equal to negative 1, what happens? I get 3 natural log of negative 1 plus 2 minus 1. It's 3 natural log of 1 minus 1. Okay, let's just do this portion for a second. That's e to the 0 is equal to 1, right? So then this portion right here, wait, I'm trying to find the right color here. This portion right here is just 0. So I've got 3 times 0 minus 1. And this is what I was mentioning about 0 don't stretch. Because I try to stretch it by 3, but it just stuck at 0. It doesn't change. But what does change, you still get that minus 1. And so minus 1 comma 0 was in fact correct, right? This is y equal to that, which is minus 1. So, oh wait, wait. Does that make sense? No, x was negative 1. Y is supposed to be... Oh, yeah. Oh, I'm sorry, guys. Shucks. So I was correct in theory, but I forgot the shift down. What am I doing? It's a good thing I checked, because I was wrong. So okay. So let's recap what we did, guys. So we did the shift 2 to the left, right? I'm gonna keep this error in here, because I think it's kind of good for you to see this process of me correcting this mistake. And I would just kind of cop out to say that I don't want to re-record this, but okay. So our shift was 2 to the left first, right? This is a shift 2 to the left, but then I forgot to do the minus 1. So 1, 2, and also 1 down. 1 down. That's the one we forgot. So 2 to the left, 1 down. Yeah. Okay, so that's the point. All right. Now that makes sense. Okay, but still, things are stretched. So kind of like a little faster than you normally would draw it, a little higher. Yeah. Instead of drawing it like, it would be otherwise like this. Okay. So now the point, this is the point -1 actually. And that does make sense, right? Because now this is y equal to 3 times 0 minus 1 is -1. So yeah, -1 does make sense as a point. Correct. Great. Good thing we caught that mistake and checked. Okay, let's clear our graph. One more to go, guys. Almost there. Okay, so what do we got here? We got another positive bigger than 1. So again, we're in this left case. We've got a -3 this time, so that's going to reflect. So just thinking about our general picture, reflection is going to make it look like, oh, sorry. This is going to go down that way instead. This is going to go up this way like that. Yeah, that would be reflection. The green is the reflection. Okay, and then I've got 4, move 4 to the left and 5 up. Now again, I am going to start with my favorite point, which is 1, 0. There's no horizontal stretching once again, but there is this vertical stretching. But once more, 0 does not stretch, right? 1, 0 does not stretch. So this is still going to be a good starting point for us. From here, it's going to move 4 to the left. 1. I'm not going to draw it like that. 1, 2, 3, 4. And then it's going to move 5 up. 1, 2, 3, 4, 5. Okay, so this is my starting point now. For sure got that, right? And at the same time, this is a good case where, okay, my vertical asymptote originally was that right at there at the center, but that should translate with me. It's going to go to the left. Yeah, so that vertical asymptote now is going to be at -1, 2, 3, -1, 2, 3, 4. This is -4. Okay, now I should be going downwards this time because I'm reflected, and also I should be stretched out. So if you think about the original thing as being something like this, that general shape, this is just kind of rough idea. Oh, let me leave that there for a second. If I think about the original one as something like this. Well, stretching out is going to reach everything faster, so it's going to be more aggressive there and then come lower down like that, quicker. Now, I would like to know maybe to get a better graph where these cross the x and y axes. Do I really want to know that? Let's do one of them. Let's do the y-axis. Should we see y-axis? Yeah. I don't know if this is worth my time, honestly, actually. I wouldn't expect you to necessarily, because it doesn't ask you to find the axes. So let's see if it comes out something easy, then we'll continue. This is where x is equal to 0. That's where you find the y-intercept, right? So if I plug in 0, what happens? Oh, it's actually going to come out nice. -3 log base 2 of 0 plus 4 is 4 plus 5. 2 to the fourth, or 2 to the second, sorry, is 4. So this part, log base 2, is just a 2. Times -3 plus 5. -3 times 2 is -6, plus 5 is -1. So I got the point 0, comma, -1. That's a useful point for me. So even though I have my general idea where it is, it's still helpful for me to kind of just get that extra point to get a better picture. It's going to look something like this. And you see it's a pretty steep compared to normal, right? Like normal, if it was just a regular old log base 2, it would look more like a little more relaxed and something more like that. Not going to get down as quickly. Okay, but there you go. That's the sketch. That's 17. All right.